Good afternoon to everybody. Welcome to our second Monday. That's all I got. A couple things. One, I realized that I messed up last lecture. Not that I made a mistake in the content, but I ended at 2 because over the summer my lectures went from 12:30 to 2. Is that right? Yeah. But here they're supposed to go from 1 to 2:20. But I saw the clock was 2. I'm like, oh shoot, I gotta end this thing. Or maybe I should say it a little more dramatically, like, I've gotta end this thing. So I did, and then I realized afterwards, I'm like, wait, I had 20 more minutes of lecture. Ended that prematurely. So anyways, if you were confused about the time, it's an 80-minute lecture normally. Last Wednesdays was an hour, but that was my bad. All part of the hiccups of settling into a new semester. So I got a couple things by way of announcements. Let's pull up Photoshop here. So we have a couple of... Okay, good. We got a couple of announcements, or I have a couple of announcements. I don't know why I refer to myself in the third person plural. It's probably a discussion I need to have with my therapist. Okay, so a couple things. First and foremost, hello. Let's see. Oh, so the first thing I want to let you guys know is that I have posted on both lecture sections a document that has all of my lecture examples. Not the answers for them, but the problems themselves. And they're all in... I think I have the first 6 chapters up on both pages, and they're all organized by what's that thing called? Chapter. So all of my chapter 2 examples are up there, all of my chapter 3 examples, etc. So you can go to Canvas, download them, and this is what I actually recommend doing. Well, first, if you're after a lecture, if you're like, oh, what was that problem? He was doing that one problem. I want to give that a try. So you can go there, look at those PDFs, download those PDFs, and they'll have all the examples. But also, and this is actually how I think they make the most effective study tool, I recommend before lecture, and the cool thing is you can do this whenever, right? Because you can watch lecture whenever. Before you watch a lecture, actually take a stab at these problems. See if you can solve them. And the cool thing is, if you've tried them already, then when I go to do them, when I engage in that specific example, you'll be able to see, either get it reinforced, like, yes, I did it right, or maybe you'll try it, get stuck, and if you get stuck, then you can be like, oh, as I work it, I'll make it to that step, and you're like, that's what I needed to do, and it actually will do more to reinforce you to attempt something that you can't figure out, get stuck, and then watch the video that'll show you how to get unstuck. That you will learn way more, and it'll reinforce things way better than if you just watch me do it flawlessly, and then you're like, oh, that's how you do it, that's easy. So I highly recommend giving those a look. Couple things that I wanted to mention with respect to our channel videos. First, I add timestamps to all of our videos, both lecture and lab office hours, the office hours that I hold during the lab section. And so in the description in each video, after I finish the stream, I go through and I look at, okay, like, what topics did we hit? Like, oh, this example, this topic, this example, this topic. And I add timestamps. So next to, there will be like a little outline with bullet points. And right next to it, in a parentheses, will be the time that that I started discussing that topic or started working that problem. And so you can go directly to that point in the video if you're like, I wanted to get repetition on sig figs. Where did he talk about that? Or maybe sig figs with multiplication. Where did he talk about that in the video? Go to the last lab lecture, look at the timestamps, you'll be able to click and jump right into that point. Also, the other reason why I do this is the lab section is 3 hours long. And I hold it as office hours, so I answer as many questions, all the questions that we have coming up. But sometimes it's like nonstop the whole way through. And you may have trouble, you may want to see one specific problem if you participated live, not know where it is in this 3 hour ocean of video. That'll help you out there. Or if you didn't watch it live, you can look at it and you may not need all of the video, but you might need 20 minutes that start at 1 hour and 48 minutes, and it'll tell you that's where that topic starts. You can jump right in. So I wanted to make everyone aware that I do that. Also, I have made 2 channel playlists. One is for lecture and one is for lab. So, and I organize that. It's under the channel page under playlists. And it'll say Chem 400 lecture fall 20 or lab fall 20. And the reason why I organize those is so you don't have to scroll back through like the entire channel that has all the videos in chronological order. You can just go, okay, like here's the lectures. Oh, that's where chapter 2 lecture starts. I'm going to start watching there. So those are some things that I do to make it easier for you to go back and kind of redigest things. And I wanted to make sure that everyone is aware of those resources. A couple things that are coming due soon. So this would be number 4. Both the lab waiver. Wait, hang on. So we've got a couple things that are due on Wednesday. At 11:59, we have the lab waiver. And safety quiz. And we have the prereq exam. Oh, exam. Both of these are due this Wednesday. So if you have been procrastinating them, putting them off, you definitely don't want to. If you don't take the prereq exam, you'll just get a 0 on it. And for the lab waiver and safety quiz, if you don't complete those and fill them out, they're not for any points, but if you don't complete them on time, you'll be dropped from the course. Your spot will be given. Your prereq. Wait, sorry. What am I saying? Your if you don't complete the lab waiver and safety quiz, you don't have to worry about losing points. There's no points attached to them. But if you don't complete them, you'll be dropped and your spot will be given to a waitlisted student. Bella, great question. So for the waitlisted students who got added, I'm going to go through and give an extension. I believe the ads went out on Friday. And so everybody who got waitlisted, I'm going to be extending your deadline so you have the same amount of time in the class to take the exam as everybody else who was enrolled. So I'll be doing that a little later today. Actually, I so appreciate the reminder. I'm going to write myself a note so I don't forget. Really, did it oh, here, hang on. Bella, forward me the email that you got your ad code, because I realized I only sent out the ones for my lab, but not everybody has me for my lab section. So whatever ad code you got, forward me that email, and I'll adjust your the due date for the prereq exam accordingly. I'm writing a note so I don't forget. Okay, let's see. Okay, a couple other. Yes, Keith. Actually, the Chapter 2 homework hasn't gone live yet, so you will be in the same boat with everybody else. Yeah, totally. Richard, that is 100% correct. If you have a lab with another instructor, you don't have to attend my lab. Even if you're in my lab, you also don't have to attend it. I just hold during the lab section, because all the lab work is basically self-study. You do the experiments, assignments on your own time, which our first experiment will be going live soon. But that's all kind of on you. So during my lab section, I just hold open office hours. Everyone's welcome to join, but nobody has to. Okay, let's see. Is the prereq exam fully graded when we get our... Yes, Bailey, that is correct. Oops. Here we go. It is. The prereq exam has no free response questions in it, so the grade you see is the grade you get, because I don't have to go back and check anything out. Totally. Okay. All right. Did I hit everything? I think I had one more thing. Let me check. Oh, yes. Okay, so, yeah, one last... oh, hang on. The last announcement that I have is tonight at the beginning of my lab section, the beginning of my stream, I will be doing a unit conversion review. Whoa, that is the weirdest N I've ever seen. I'll be doing it at the beginning of the lab section, so anybody who wants to drop by, get a review on unit conversions, which is one of the main topics of the prereq exam, feel free to do so. Yeah, so that is my last piece of information. Okay, let's see. Okay, Jared, I have not put up any homework yet. It'll be coming soon with an appropriate due date. The due date for everything on the tentative lecture schedule is also predicated on me getting everything out in a timely fashion. If I get an assignment out later, I will extend the due date accordingly. But right now it's not up. Priority number one is getting the first lab experiment up. And yeah, okay, let's see. Is there a way to see the mistakes after we take the exam? Oops. Let's see. Yes, Kyle, that is 100% correct. The exercise 1 assignment for lab is an excellent review for the prereq exam, because exercise 1 is about algebra, unit conversions, and significant figures, and that is everything that the prereq exam covers. Okay, Christina, should we keep checking in with you if you're still on the wait list? Or will you let us know if we will or will not be added? Okay, so our first batch of ad codes went out on, well, I think mine went out on Thursday. I don't know when the other lab sections sent them out, For all of you who are still waitlisted, the deadline to add is the 6th of September. So at this point, every lab class is enrolled to its maximum. And so at this point, we have no more space, but the prereq exam ends on the 2nd for most of the class, except the people who just added. And so that may result in more drops. If more people drop, then fresh ad codes will be sent out. But if not, then not. So if you haven't received one yet, it's because we've enrolled to the max, but we don't have any more space. Some may open up this week, but after this week, it'll be too late to add. So this is kind of our last go of it. All right, let's see. Yes, Jared, that is totally to be expected. It'll be coming out. The first lab should be going live this week, and then homework will be coming out soon after. Let's see. Exercise 1. I'd say so. If yep, totally. Exercise 1 on the lab page. All right, does that go for all labs or just yours? All the labs at this point. Christina, and then let's see, Anthony. What is the rule for sniffing? Okay, Anthony, that is a great question. Okay, so let's go ahead and all these questions have been great. I realize that there's on the front side of the semester, there's always kind of it's front loaded with procedural questions. Let's go ahead and dive into lecture, especially now that we're 20 minutes behind. Okay, so we were talking about the periodic table. And where we left things, we had discussed the how to identify metals and non-metals. You'll recall the tip that I gave is draw a line right under boron and aluminum, and everything on this side of the line, plus hydrogen, where your nonmetals by this side. I realize I said this side. You're like, which side? The right side. Right of that line are your nonmetals and hydrogen. Left of your line are all your metals, and then everything touching that line are your metalloids that have some metallic properties and some non-metallic properties. That is one useful way to divide up the periodic table, but it is not the only way. All right. Another way you can divide up the periodic table is you'll notice that you kind of have these two kind of cliffs on the periodic table, these two sections that are higher than the rest, and then you kind of have this ocean down below right here, kind of coming in between them. The two high rises, these are together, this side and this side are known as the main group. These are our main group elements. And then the kind of ocean in between them, separating them, these are called the transition metals. And we'll have a lot more to say about them soon. This little island floating down by itself, not connected to anything. These are your lanthanides. And actinides. Again, you don't have to memorize these, but the reason why I'm introducing them is you should kind of low-key know them how to break up the periodic table, so that when I say main group elements, you're like, oh, those are the two tall sides. When I say transition metals, you're like, oh, that's that space in between. When I talk about lanthanides and actinides, which I won't talk about them that much, those are right down there in the bottom. All right. In addition, so there's a bunch of different kind of special groups of elements on the periodic table. The only one that I'm going to mention by name are these guys right here at the end. These are our noble gases, and we will be doing a ton with these dudes. They are the most stable set of elements on the periodic table. They're inert, which is another way of saying unreactive, and unreactive is another way of saying stable. These are very, very, very stable, so much so that many of the elements on the periodic table seek to emulate them in their electronic structure. They desire that stability, and they will react with other things to gain that stability. We'll spend a bunch of time talking about that in the coming weeks. I'm not gonna make you memorize the halogens or the alkali metals or the alkali earth metals or any of those things, but you do need to know that last column on the periodic table, helium, right here, all the way through the original gangster down here. Those are your noble gases. All right. Finally, there is one last division of the periodic table that we need to go over, and that is the periodic table can be divided up into blocks. All right. The first two columns on the periodic table, this is called the S block. All right. The transition metals right here represent the D block. All right. The other side of the main group, these guys over here, this is known as the P block. And finally underneath, these are the lanthanides and actinides together form the F block. This will become, knowing the blocks of the periodic table will be useful to us when we talk about electron configurations a little bit later this semester. So, excuse me, we won't be using the block nomenclature right now, but in the future we totally will be. So that'll pay dividends a little bit later this semester, but I just wanted to introduce that now. All right. So we are, if you can believe it, almost done with chapter 2 at this point. We just have one last topic to cover. A topic that will live in infamy and something that will definitely strike your memory, if not your imagination, from your prerequisite course. We have to talk about the mole. All right. This is usually, and I don't have the benefit of this, but when classes used to be live in person, whenever I would say the mole, there'd usually be a ripple of groans that would kind of roll through the class, and that's because I think a lot of people have had bad experiences with moles and stoichiometry, and they're like, oh, I just remember doing it over and over and over in my prereq course. And if you did, that's good, because it was preparing you for this. You will be using this concept and doing these types of calculations over and over and over. So let's go ahead and get into it. So first question we want to ask is, what is a mole, right? And a mole is not just a small, blind or poorly sighted burrowing creature, though if you're ever bored, do a Google image search. That's my Sean Connery impersonation. Do a Google image search of a star-nosed mole. If you've never seen one of these things, they're incredible. It's like a mole that rear-ended an octopus with its nose. It's like got an octopus. It's got all these weird tentacles right on the end of its face. Check it out. It's bizarre and beautiful all at once. But a mole, we're not just talking about the small burrowing creature, especially in a context of a chemistry class. A mole, conceptually, is very similar to one pair. All right, if I asked you what is a pair is just two things. All right? If I asked you, so if I had told you I had a pair of shoes, you'd be like, oh, two shoes. A mole is very similar to 1 dozen conceptually. If you have a dozen donuts, that means you have 12 things, right? Unless you have a baker's dozen. Then it's 13. A mole is the exact same idea as these two, but it's just a whole lot more things. So 1 mole is 6.022 times 10 to the 23rd things. All right? That's all a mole is. Now, the reason why I've gone vague with things, the types of things that you'll run into that moles can represent. 1 mole can be atoms, molecules, ions, or really particles of any kind. All right, that is what we're talking about when we're talking about things. So 1 mole can be 6.022 times 10 to the 23rd atoms, or ions, or electrons, or photons, or water molecules. Any type of thing like that. That's what I mean by thing. All right, so that is what a mole is. Now, let's do a few examples. Starting with how many atoms are in a sample of, where are we, carbon, that has 3.2 moles of carbon. All right. Now this is an example of a unit conversion. All right. So, and if this process is unfamiliar to you, how to use ratios to convert units, I'll be doing a review of that lab lecture tonight, so you can check that out at 7 or later at your own convenience. But we have 3.2 moles of carbon, and we need to convert to atoms of carbon. All right? Before we even think about numbers, because often this is where I would get confused as a student. This is where I see confusion kind of enter in as an instructor with students in my classes. They're like, do I multiply by 6.022 times 10 to the 23rd? Do I divide by it? I can never remember. Don't even think about the numbers. First, just line up your units so they can cancel. We want to put moles of carbon in the denominator, and we want to convert to atoms of carbon, right? And so we've lined up moles of carbon to cancel, and we've set ourselves up to have atoms of carbon left over, all right? Once you have your unit set up to work out the way you want them to, now add the numbers. 1 mole is 6.022 times 10 to the 23rd atoms in this case, right? It can be things. In this case, things are atoms of carbon. The 6.022 times 10 to the 23rd is called Avogadro's number, by the way. So if you hear me throw out Avogadro's number, that's what I'm talking about. All right, so we've already set this up, so moles of carbon will cancel. Now we need to crunch some numbers. So let's do this. 3.2 times 6.022 times 10 to the 23rd. My value that I'm getting, my calculator is telling me that the answer is 1.92704 times 10 to the 24th. All right? But this is only 1/3 of my answer. Remember, an answer has 3 parts. There's the value, which we have, then the units, and the sig figs, all right? So we need to add units and figure out how many significant figures we can have. Our conversion factor has 4 significant digits. There's 1, 2, 3, 4 sig figs in 6.022. If you need a review of that, check out last Wednesday's lab lecture. We go into all of that information. So we've got 4 sig figs in 6.022. We have 2 sig figs in our sample of moles. So our answer can only have 2 sig figs. We count off the first 2. 2 is a number that rounds down. So the correct value with the correct number of sig figs will be 1.9 times 10 to the 24th. And then the correct units here are atoms of carbon. So there are 1.9 times 10 to the 24th atoms of carbon in a 3.2 mole sample of carbon. All right, let's do another example. So we got to get some reps in here. All right, how many moles of carbon are in a sample with 13.0 times 10 to the 8th atoms of carbon? All right, this is the same unit conversion, just moving in the opposite direction. All right, so we're given atoms of carbon that we have 13.08 times 10 to the 8th atoms, and we need to convert this to moles. So we're going to put atoms of carbon, amtas, there we go, atoms. So we got atoms of carbon in our denominator, moles of carbon in our numerator. Now that we've lined up our units, right, atoms will cancel atoms. Now we add in our numbers. 1 mole of carbon is 6.022 times 10 to the 23rd atoms. All right, so atoms of carbon cancel. We're left with moles of carbon, which is great because that's what we were asked to solve for in this problem. And now we have to divide one by another. All right, so my calculator is telling me that my value is 2.15875,125 times 10 to the negative 15th moles of carbon, right? That is my correct unit because that is the unit left over. We've got the correct units, we've got the correct values. Now we have to look at our sig figs. Again, Avogadro's number has 4 sig figs, but our initial measurement of atoms only has 3. So our answer can only have 1, 2, 3. Count off the first 3. 8 is a number that will round up. So our final answer 2.15 times 10 to the negative 15 moles of carbon has the correct value, the correct units, and the correct significant figures. All right, and so that is the solution to that example. All right, now those were two kind of like warm-up examples, but they really do not highlight why moles are important in a chemical context. Okay, so why are moles important? Here's why. If you look up, for example, if you look up the atomic mass for carbon, right? You look it up, and on the periodic table will tell you that the atomic mass for carbon, the atomic mass for carbon is 12.01. Depending upon the periodic table, you may have more or even fewer sig figs, but 12.01. Many periodic tables display that. Now, what are the units here? 12.01 watts. Well, as we've discussed previously in this class, these come in atomic mass units. All right, atomic mass units. Now that is true, and that is a real mass unit, and it is. Oh, sorry. Hang on. Sorry, I just saw the questions. Andrew, Lena, Bella, and everybody else who's sitting in your chairs asking, wait, shouldn't I round up? The answer is yes. Yes, you guys totally rock, right? I even said, look, I'm an idiot. I was like, whoops, nope, let's go here. I said 8 rounds up. Then why didn't I? Right? It's not 2.15 times 10 to the 15. It's 2.16 times 10 to the 50 moles of carbon. Thank you so much. Excellent catch. Because rounding up means you actually round up, right? Thank you. Okay. All right, so you look up the atomic mass for carbon on the periodic table. 12.01 AMU, right? Totally correct. That's right. But what I haven't told you is that 1 AMU tells you the number of grams in a 1 mole sample. 1 AMU equals 1 gram per mole. All right, these two are equivalent units. AMU is another way of saying grams per mole. And this gives us a wealth of information. Now, every atomic mass on the periodic table can become a unit conversion because it tells you that there are 12.1 grams of carbon in 1 mole of carbon, or it tells you that in a 1 mole sample of carbon, will have a mass of 12 grams. All right, and these unit conversions pay dividends. All right, we will be using these all throughout the semester. They allow us to solve problems like the following. All right, let's check this out. So let's do the following example. how many atoms are in a 5.06 gram sample of copper? All right, how many atoms are in a 5.06 gram sample? All right, now, we do not have a unit conversion to go straight from grams to atoms. I don't know what that is. But I do know that, actually, hang on. I do know that on the periodic table, copper has an atomic mass of, oh, I don't have it written down, but I have a periodic table here. Oh, which doesn't have atomic masses. Hang on. I'm like, I know the atomic mass for copper. Doesn't know the atomic mass for copper. Where are we? There you go, 63.55. Copper has an atomic mass of 63.55 grams per mole. So I can use the atomic mass of copper to convert my grams of copper to moles of copper, and then I can use Avogadro's number to convert moles of copper to atoms of copper. So this will be a two-step unit conversion, and you execute it like so. You start with 5.06 grams of copper. In our first step, we need to convert grams of copper to moles of copper, all right? And we use the atomic mass, which tells us that there are 63.55 grams of copper in 1 mole, all right? So grams of copper cancels grams of copper. And then in a second step, we can use Avogadro's number to convert from moles of copper to atoms of copper. All right? And here we use Avogadro's number because we know that a 1 mole sample of copper has 6.022 times 10 to the 23rd atoms. And now moles of copper cancel moles of copper. We're left with atoms, which is what we're after. And now we're ready to crunch our numbers. All right. So let's clear this all out. 5.06 divided by 63.55 times 6.022 times 10 to the 23rd. All right, so our value here I'm getting from my calculator is 4.794856 times 10 to the 22nd. All right, that's my value, but now we need to look at our significant figures. Avogadro's number has 4. You can see that our atomic mass has 4 sig figs, but our initial mass only has 3, so we can only keep 1, 2, 3. 4 rounds down, so our correct value with the correct sig figs will be 4.79 times 10 to the 22nd, and then the correct units are atoms of copper. All right, so there are 4.79 times 10 to the 22nd atoms of copper in a 5.06 gram sample. All right. Let's see. Okay. So I have one more example to share And this example, there's a couple things about this one. This is a boss level. All right. This is a boss level challenge. So this problem is a step above the problems that we've been doing. So this will be a particular challenge. Because this one is so challenging, I'm actually not going to do this one. Not because I'm afraid of it, not because I don't want to work a hard problem, but because I want you to try this on your own. See if you can solve this one. Try this one on your own. And then ask me about it in office hours. Come to office hours, ask me about it. We can work through it together. You can see if you got the right answer. But I think there's a value in trying something and walking out on a tightrope without a safety net, rather than passively watching me do something that's hard. Because here's the thing. I took Gen Chem. This is going to date me. But my first year of college, fresh out of high school, in the fall of 2005. So I took this 15 years ago. And I've been doing nothing but chemistry since. So when you watch me work a hard problem, it won't look like a challenge because you're watching me do it. It'll be the same thing as a toddler or an infant watching a 15-year-old walk. Like I've got a 2-year-old, right? If my 2-year-old watches my 15-year-old nephew run up the stairs, the 2-year-old could think like, oh my gosh, that's easy. I could do that because I just saw my 15-year-old cousin do it. He's been doing it a lot longer. So actually taking that step to try it on your own is an important part of learning. And so I'm going to leave it with you, but I'm not leaving you totally alone and cold. Bring it up in office hours. Come ask me about it later. After you give it a try, we'll do it together. You'll learn a lot more. All right. So that's enough of a preamble. Let me pose the question to you. How many molecules of water are in a 1.00 milliliter sample of water? And then note, you will need this note to solve. The density of water is 1.008 grams per milliliter. All right? This is a next level problem. It's a step beyond anything we've done. Try it on your own. Come back to me, bring it back up, and we will work through it together. All right, that is the end of chapter 2. We are ready to dive on in to chapter 3. All right, chapter 3. Now, Kate, great question. All right. So in chapter 3, we are going to dive headlong into study and discussion of molecules. All right. We're going to be talking about them for a while, and so before we get in to that discussion, there's a few things that that we need to go over. So the first is kind of, I'm going to give you a general kind of breakdown of matter. All right. We're going to spend all of chapter 3 talking about pure substances. All right, pure substances. And pure substances can be broken down into two general categories. Those categories are elements and compounds. All right, elements have all atoms are the same type. All right, and compounds have atoms of different types. All right, that is the difference between an element and a compound. Now, elements actually, I need to give myself a little more room to work here. That's good. So when it comes to elements, elements can be further broken down into either atomic elements or molecular. All right, atomic elements would be, for example, like copper we just talked about, or gold, which is Au. If you have copper wire, it's just a bunch of copper atoms all smushed together, all lined up together. Same with like your gold ring or whatnot, assuming it's not an amalgam of something, which actually with gold it usually is. But if you have pure gold, it's just gold atoms all together. Molecular elements are elements like our what are called homonuclear diatomics. So hydrogen, for example, doesn't exist in nature as just H. It's H2, right? Nitrogen, N2, oxygen is O2, fluorine, chlorine, bromine, iodine. These are all elements because there's only one type of atom, but they're molecular elements because it's not an individual atom. They're in a molecule with other types, all right? These in particular you should watch out for in problems. Normally, I tell my class to memorize them. You don't necessarily need to memorize them because all your exams are open, everything, but it will save you time if you just know these are your diatomic elements. Which actually, if we're going to take just a brief interlude, if you want to know where your diatomic elements are, so there's hydrogen, which is just right here, but all the rest of them, oops, messed that up. All the rest of them are right here. These are all your diatomic. So you can use the periodic table to remember it's mostly right here in this corner of the periodic table, plus hydrogen. All right, so that's where those things lie. Okay, so those are elements, atomic and molecular. Now, as far as compounds go, there are also compounds also come in two flavors. There are ionic compounds and covalent compounds. I guess it's a little redundant to write compound after this since they're already in the compound heading. and we will spend more time talking about ionic and covalent compounds. We'll spend a ton of time learning how to name them. But I just kind of wanted to give you kind of a general kind of outlook and categorization scheme for how to look at and think about different types of pure substances. And again, chapter 3, we're going to be focusing on molecules. All right. Now, there are a couple different ways to depict atoms and not atoms, mostly molecules. And these are called formula. All right. You could have, for example, there's what's called the empirical formula. See, this is why you never change your answers. I was like empirical with 2 I's, and then I'm like, no, maybe it should be an A. Turns out it's an I. The empirical formula, always go with your first response. The empirical formula is the simplest whole number ratio between the atoms in a molecule or compound. All right, the simplest whole number ratio. This is contrasted with the molecular formula. The molecular formula is the atom count of each element in a compound followed by what's known as the structural formula. All right, the structural formula is a depiction showing the connectivity. I'm not going to have room for connectivity there. The connectivity and bond order between all atoms in a compound. All right. Now these 3 different depictions, they're ordered in terms of increasing information. So an empirical formula gives you very little. It's just the structural, the whole number ratio between the elements present. Molecular formula, total atom count for every element. And then the structural formula shows you how they're connected, what atoms are attached to what atoms. And so it's very information rich, whereas the empirical formula is very information lean. Now, to give you kind of like an example of the 3 kind of live, you've got the empirical formula, the molecular formula, and the structural. All right, so you could have a compound that has an empirical formula with a 1-to-1 ratio between carbon and hydrogen. All right? 1-to-1 ratio. This could have a molecular formula equal to C4H4, for example. And then a structural formula that would look like this. Right, and you can see there's an increasing amount of information. First just a ratio, then atom counts. Now we can see like, oh, there's single bonds, there's double bonds, which atoms are bonded and how they're bonded to each other atom in the molecule. But this molecule, C4H4, is not the only molecule with a 1-to-1 carbon to hydrogen ratio. For example, you could have a compound whose empirical formula is the same, but whose molecular and structural formulas are different. This could also be C6H6, which would have a structural formula that looks like this. Oops, I messed that up. There we go. All right, C6H6, C4H4, two different molecules with the same empirical formula. That can totally happen. Another thing you should be aware of is the empirical formula and the molecular formula are not necessarily different. For example, carbon tetrachloride, CCl4, carbon tetrachloride is a molecule with 1 carbon and 4 chlorines. Its structural formula looks like this. Sorry, takes a little bit to draw in all the lone pairs. All right, that's the structural formula. Here's the molecular formula. But you'll notice that in the molecular formula, we've got a ratio here of 1 to 4. That's already in its simplest whole number ratio, right? There's no common factor there. So for carbon tetrachloride, the empirical formula is the same as the molecular formula. That's also a possibility. You can have two different molecules with the same empirical formula. You can also have molecules that have the same molecular formula and empirical formula. All right. Now, we're going to be leaning on these heavily. Probably review, definitely review. You probably remember how to write a chemical formula from your prerequisite course. But I just wanted to cover it so we're all on the same page. All right. Now we are going to spend quite a bit of time, the remainder of today's lecture and then Wednesday's lecture, talking about nomenclature. And we're going to start with ionic compounds. So ionic nomenclature. Oops. We'll make our E green. Nomenclature is naming, all right? So we're about to learn the naming of things, all right? Now, when you are naming an ionic compound, well, first, let's just talk about what an ionic compound is. All right, an ionic compound is a compound comprised of at least one cation and one anion. At least. They could have multiple cations, there could be multiple anions, but there's at least one of each type. All right? Now, if you're wondering what a cation is, a cation is a positively charged ion. And an anion is a negatively charged. A negatively charged ion. All right, so we've got a positively charged ion, a negatively charged ion. That is what your cation and anions are. Now, when it comes to naming ionic compounds, there we go. So when we talk about naming, it's fairly straightforward. You start. You name your ionic compound by stating the cation name followed by the anion name. So the cation element name followed by the anion element name with an added "-ide". At the end of the anion element's name. All right? So, looking at it, it can look a little abstract. I find the best way to learn this is just to dive in and start doing some examples. Oh, Peter, how's it going? Let's see. Okay, so let's dive in and do some examples. Name each ionic compound. All right, and let's start with sodium chloride. All right. I realized I missed a little something in my notes. You may be going, how do I know it's an ionic compound? And if you're asking that to yourself, that is a totally legit question. And here's a partial answer. An ionic the way you'll be able to spot an ionic compound is you'll have a metal plus a non-metal together in the same compound. They'll be together in the same compound like 98% of the time. And the second I say that, there's always this kind of like zeroing in where it's like, wait a minute, if it's 98% of the time it's a metal with a non-metal, what about that 2%? And I just want you to roll with me on this. Let's not think about the 2%. Let's just focus on the 98% of the time. It's metal plus non-metal. I will bring it up in a little bit, probably in Wednesday's lecture. And when I do, you'll be like, oh, that makes sense. I know that. But for now, let's just think metal with non-metal. That's what makes it ionic. And when I come to reveal the exception, that 2% of the time when it's not, it's going to be an of course moment for you. All right. So just trust me, trust me on that, and roll with me with these next few examples. So we want to name sodium chloride. All right. I'm sorry. I just named it for us. We want to name this compound. Let's pretend I didn't just say the name out loud, and use what we know about naming to solve this thing. So, Na is the metal sodium. Cl is the nonmetal chlorine. But we're going to axe that ending and call it chloride. Salt. Andrew Jones. Very good. This is table salt. Chemical formula name, sodium, not sodium chlorine, sodium chloride. All right. Let's do another example. I'm going to give myself just a little bit more room on this slide. All right, let's name another one. Let's do MgBr2. All right, our cation name, Mg, is magnesium. Our anion's name, well, the element is bromine. So to get our anion name, we axe that ending and add an ide. So this would be magnesium bromide, all right? And finally, L2O3, let's name this dude. Again, cation always comes first, and this cation is aluminum. Our anion, well, the element is whoa, hang on. Promise I can spell oxygen. Oxygen. And oxygen's anion name, we axe that ending, not an ide. This is aluminum oxide. All right. Now you'll notice, I want to draw your attention to something. Sodium chloride has a 1-to-1 ratio, right? Of elements, 1-to-1. Magnesium's a 1-to-2 ratio. Aluminum oxide, or sorry, magnesium bromide's a 1-to-2. Aluminum oxide has a 2-to-3 ratio. Not the ratio of elements in your ionic compound does not translate into how you name it. All right. The reason why we're starting with ionic compounds is they're simple. It's always cation name, anion name, right? Magnesium bromide, aluminum oxide, sodium chloride. It doesn't matter how many of each element are present. That, we will get into that when it comes to naming covalent compounds, okay? But for ionic compounds, it's simple. Just bump, bump. You don't have to worry about the numbers. Now, I'm going to take a minute to set up where we're going next lecture. With these 3 examples that we just did, I gave you a chemical formula and asked you for a name. All right? But how about going in the other direction? What if I asked you to write the chemical formula for potassium iodide. All right, for potassium iodide. Now, here's the trouble. The cool thing when you're given a formula and you're asked to name it is like, I don't have to worry about the numbers. It's just name, cation name, anion name. But when you're given a name, how do you figure out how many of each element to include? We know potassium has the atomic symbol K. We know iodide is the anion for iodine, so it has the symbol I. But the name doesn't explicitly tell us whether they come together in a 1-to-1 ratio, for example, whether it's just Ki. Is it K? Is it Ki? Is it K2I? Is it Ki2? Is it K2I3? The name doesn't explicitly state it. The way you get out of this quandary is you got to look to the periodic table. And on Wednesday, in lecture, we will learn how to use the periodic table to determine the cationic charge of a main group element or the anionic charge of a main group element, and those charges will tell us the ratio in which they come together. All right, so tune in Wednesday for that information. Let's see. Emma and Andrew, spot on. Great question. Whenever you're naming an ionic compound, it's always cation first, then anion. So it's always positive boy, negative boy. All right, always cation, then the anion. And so that's not a coincidence, because that's the correct way to do things. All right, so we're going to go ahead and wrap up lecture here. We'll pick up Wednesday with more ionic nomenclature and see how far that adventure takes us. Cool dudes, thanks for tuning in. I'll see some of you possibly tonight in office hours. I'll be doing a lab lecture on unit conversions, and then if I don't see you in lecture tonight, I'll see you. Sorry, if I don't see you in lab/office hours tonight, I'll see you in lecture on